Okay, so here we are talking about something that's called the sodium-potassium pump. And this is another transmembrane protein. And this is something that is considered what we would call active transport. And so a key difference between this and the channels, the voltage-gated channels, is that those channels are just sort of passive open spaces that let ions flow through them, and they're powered by the concentration gradient and the electrostatic force. But these active transports are proteins that require constant energy input for them to work. And so let's see what that is. And so these are constantly active. And so let's pretend like we just had an action potential. Sodium has flooded into the cell, and potassium has left the cell. And so we're right there at that period during falling action, during the falling phase, and that hyperpolarization. And we need to get back to the resting membrane potential so that our voltage-gated channels are ready to go again. That if they open, then we get the same sort of flow of sodium. So sodium must get back outside of the cell. Potassium must get back in if we were to ever have another action potential. So enter these scary-looking, like alligator chomper potassium channels. And so these are channels that specifically bind and fit sodium and potassium ions. Specifically, each channel at a time binds three sodium ions. And it's got another little domain down here that will bind something called ATP. That is adenosine, so that's an N, triphosphate. And so this is a molecule that has adenosine, and three phosphates. And so let's make our adenosine here gold to separate it out. And so adenosine that has these phosphate bonds here, which are our phosphate group. Oxygen, phosphate, oxygen, and a third phosphate. So this is the chemical chain there. We've got some double bonded oxygens up here. And so these are bonds that have a lot of energy, the bonds between the phosphate and the oxygen here. And so if you cleave these, so if I cleave that to get a separate phosphate group, by breaking that bond, you also release a lot of energy, because the electrons in this state are in like a higher energy state. They're in one of those higher orbital clouds. And if you break it, the electrons go back down to a more comfortable energy state. So right now there's a lot of potential energy, sort of like a ball on top of a building or a cliff. It potentially could fall down to a more resting state on the ground. And so that energy can be used to change the conformation of this. And that's exactly what it does. ATP binds. It's cleaved. A phosphate group is cleaved off. So we got our little, however I want to draw them. energy explosion in the cell. Energy is released, and we end up with our ADP. Alright, so ADP, adenosine diphosphate, because there's only 2 now instead of 3. That energy changes the conformation here, opens it up to the extracellular space, and so sodium moves out. And all that potassium that was on the outside of the cell through the voltage-gated channels now is attracted inside and binds to our pump. 2 to be exact. Now, moving down in time here, our phosphate group has come off to be recycled to ATP again, and we revert back to our original conformation. And remember, we bound some potassium, and that change in conformation sort of boots out our potassium into the intracellular space. So, with one sort of cycle of our potassium-sodium pump, we have taken 3 sodium out of the cell, and we have moved in to potassium. And so if we're thinking about our intracellular space, we've subtracted 3 and we've added 2. -3, +2. And so that gives us, that equals a net charge of -1. We do this a bunch of times, and this is what drives the resting membrane potential to be negative. -65. All because of the potassium pump working tirelessly to get us back to our resting membrane potential. Non-stop. Getting the appropriate conditions so that once again we can initiate an action potential. All driven by these concentration gradients. Tons of sodium outside of the cell. Tons of potassium inside. Just waiting for those voltage-gated channels to open. Okay, so there's our whirlwind fundamentals of our action potential there. Understanding through the voltage clamp, getting an idea of how it functions and what ions might be included. Sort of a gross anatomical view of the propagation of the action potential down the axon. Took a close look at our voltage-gated channels that allow the axon to initiate spike in action potential and eventually get back to resting membrane potential, and our tireless sodium-potassium pump constantly moving sodium and potassium outside to inside the cell respectively. Thank you.